All right, my friends, let's take a look here at problem 6. Probably the most conservative way to figure it out would be to go ahead and just graph it, at least as far as the limit value piece is concerned. So if you were to graph this piecewise defined function, you'd basically graph y equals x squared minus 4 over x minus 2 at everywhere but x equal to 2. But then when x is 2, you just pull out the point 2, 1. So if we simplify this function, you would end up with, like if you factor the top and cancel it with the bottom, you'd end up with this. But remember, so you get a line graph, right? But you graph it everywhere but at 2. So visually speaking, boop, 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 boop. So you basically get a line graph with a y-intercept of 2, a slope of 1, and then it just has an infinitely small hole where x would have been 2. So where's that hole? It's at the point 2, 4. Okay, and then the graph of f would then also have the point 2, 1 on it. Okay, so let's look at this in a couple little pieces here. So does f have a limit at x equals 2? Well, a limit meaning a double-sided limit. And so what would the right-sided limit be at 2? It would be 4. What would the left-sided limit be at 2? It would be 4. And so we would say the double-sided limit of the function f at 2 would be 4. So I'll write that down. The limit as x approaches 2 of this function would be 4. Remember, a double-sided limit at a target number like 2 here will only exist if the left and right-sided limits at that target number both exist and both equal the same thing. So I would definitely rule option 1 in. Now I hope visually the graph would tell you that this function is not continuous at 2. A really basic way to describe continuity is as you draw the graph, if you ever have to pick up your writing device and put it back down to draw it, then you have a discontinuity. So f is not continuous at x equals 2. Now for 3, honestly, at this point, I think we could probably, if you were confused about 3, the fact that you know 1 is true and 2 isn't would have led you to choose A just by using the process of elimination. There's no option that says 1 and 3 only. However, let's make sure you also can rule 3 out in a different way. Just a note for this one. If you recall, the definition of the derivative at a single point was defined as f prime of c equals the limit as x approaches c of f of x minus f of c all over x minus c. And so basically within this definition of the function, you have the point c f of c that must be attained on that function at the target number. And so here the target number was 2, but the point 24 was never attained because there was a discontinuity. So basically, if a function isn't continuous at a number, it cannot be differentiable at that number. I'm going to say that again. If a function is not continuous at a target number, then it is also not differentiable there. And it has to do with this definition of the derivative at a single point. So we could rule 3 out, and then you would get either by process of elimination or just very legitimately understanding the concepts, you could get that the correct answer was A to this one. Hope that makes sense.